Remember, what we've done here is set up a local home automation controller which can communicate with other devices plugged into the controller, including the host site's internet. This internet access is useful so that the local controller can communicate with cloud devices such as, Amazon voice services. This Wi-Fi connection is or internet connection is also useful on the local network so that the home automation software can be accessed by phone or computer, provided that user has the Home Assistant password and is on the local network. The internet access is also useful if you wanted to access the Home Assistant build remotely, off site. Um, However, users will still be concerned about their internet privacy, and at the very least, they'd like to keep the smart home internet device access to a minimum in the interest of internet safety. So, for the next few devices that will have wireless communication, we're actually going to register them on a different wireless network, one powered by a USB stick that's called a Z stick for the Z-Wave wireless network. And we'll be plugging it into the Raspberry Pi. Cloud services, as well as other proprietary services, can have extensive functions, but they can also be relatively limited functions. Now consider the differences between a non-programmable thermostat and a programmable thermostat. The non-programmable thermostat can adjust the temperature, but the programmable thermostat can be zoned for each hour of the day and each day of the week. But if I want a programmable thermostat that can be programmed for each hour of the day for every day of the year, I would need something a little bit more capable. And even a $300 smart thermostat like the Rheem EcoNet only has 7-day programming, whereas I want programming for every hour of the day, every day of the year, with even further flexibility to accommodate a variety of on-site energy issues, such as renewable energy or battery storage, and also the ability to save the customer money through advanced automation. So even the $300 Rheem smart thermostat, particularly because they do not have an open API or open communication to a variety of smart hubs and smart platforms, they have a closed network, and so the $300 Rheem thermostat is not good enough for my. In search of my smart thermostat, what I did was to search for Z-Wave thermostats under the assumption that a Z-Wave thermostat would be a smart thermostat. A myriad of options were available to me on eBay. With any smart device, the version of the software is important. So Z-Wave is now on a Z-Wave Plus version of its technology, and I recommend sticking to Z-Wave Plus components for Z-Wave communication. I would also consider Zigbee as opposed to Z-Wave, as well as Wi-Fi components, so long as they were compatible with my home automation software, and we'll talk more about that later. I chose Z-Wave because traditionally Z-Wave has been cheaper than Wi-Fi devices, but also more intelligent. Well, now many Wi-Fi devices, particularly thermostats, can be found at similar price points and functionality. I would caution that Z-Wave devices can be more difficult to install than their Wi-Fi counterparts, but that does come with some increased functionality, such as the ability to stay off the home's internet completely. At any rate, I went with a $65 Z-Wave Plus thermostat and decided to swap it out with my existing non-programmable Honeywell. Now, remember that National Electric Code defines a qualified person As one who has the skills and knowledge related to construction and operation of electrical equipment and installations, and has received safety training to recognize and avoid hazards involved. So if you are a solar installer and you think you can simply take the thermostat off the wall, you might be surprised to know that it could short out a fuse in the air handler so that the fan will not turn on after you install the new thermostat. This kind of thing is avoided by remember to doing things safely, like powering down the equipment that you are working on before servicing it. But installing the thermostat is fairly straightforward, requiring knowledge of the HVAC system to determine whether or not the home has gas or electric heat, as well as the kind of electric heat provided. The wiring is a little bit tedious. Now, I was working on a larger home where a Google Nest was installed but wasn't working. The air conditioning contractor had not wired the indoor and outdoor unit to accommodate the standard 8-wire thermostat configuration, and so the Nest was not compatible with the Rheem unit. Rheem had their own $300 programmable thermostat that did not need all of those wires to function, but the end result was that the use of that thermostat locked the user into a thermostat that was not programmable from an outside source, and the thermostat only had day of week functions. So that's a shame because the thermostat on a solar home should be able to adjust with solar production to better manage the intermittent energy produced on site, as well as to manage consumption. But in my case, I want a thermostat to be programmable by time of day for each day of the entire year. Now, here's my thermostat within my home automation software. It has similar functionality to a Nest. A wall-mounted tablet could serve as a dedicated thermostat controller instead of a real thermostat or a hardwired thermostat, while also controlling other functions such as home media players or the lights in the room. To be clear, my Z-Wave thermostat does not provide this level of capability on its own. The Internet of Things has enabled this software to be applied to my $40 thermostat. My utility offers a time of use rate structure, which increases my electricity cost by 400% for 2 to 3 hours per day. It then decreases my rate for the remaining hours by 50%. So if I keep my peak energy use to a minimum, I could save a lot of money. Now, a programmable thermostat could help save money in this manner under a time of use rate without being smart, but a 100% non-programmable thermostat, one that only adjusts the temperature settings, cannot take advantage of time of use metering. So many programmable thermostats can be programmed by hour of the day and day of the week, albeit with some difficulty. But my summer peak times are from 3 to 6 p.m., whereas my winter peak hours are from 6 to 8 a.m., with weekends being off peak. So I'd prefer a thermostat which can be programmed for each hour of the day, each day of the year, in order to avoid having to reprogram it every 6 months. But a simple day of the week, time of day thermostat could work as well without being smart per se. The most important features are the hours of the day and day of the week programming capability. However, the cheapest programmable thermostat I found was $20, and the cheapest smart Z-Wave thermostat was $40, and so I thought that was a reasonable upgrade to pay for additional smart capabilities. Now, the cheapest name brand Wi-Fi option thermostat was $90, whereas most of the top shelf options ranged from $150 on up. I went with a $65 Z-Wave option. So within my smart home software, I have a home automation menu. I have an automation to turn the thermostat on and off between the hours of 6 a.m. and 8 a.m., which prevents my air conditioner from running during those times. The thermostat is programmed to turn off at 6 a.m., wait for 2 hours, and then turn back on again at 8. I have smart wall plugs which are similarly programmed, allowing me to turn my always on dehumidifier off during peak times and then right back on again when those times are over. So my refrigerator does the same thing. It will run only a small amount during peak times. And my hot water for winter coffee is on a smart plug that is turned on precisely at 5:55 a.m. in order to be hot but avoid peak use. 240 volt smart relays can similarly control 40 amp electric tank water heaters. So, controlling energy use in this manner can have substantial savings. By switching to my utility's time of use metering plan and using load shifting to reduce or eliminate my air conditioning loads, refrigerator loads, and using other 120 volt devices to reduce 120 volt loads, I can save 20% on my electric bill through my utility time of use rate structure without any substantial changes to my lifestyle. But Home Assistant is just software. It needs some hardware to host it. The combination of hardware and software to host a smart home is called a hub. Some hubs require internet to function. Other cloud devices may communicate directly with some remote Amazon computer somewhere and not need a hub physically installed in the home. Some hubs that benefit from internet connection can also work locally without internet to control those same devices locally, which means they would still work during an internet failure unless the internet company has some back-end fail-safe to prevent that from happening. Some internet hubs have backup internet connections, like security alarm systems that come with their own data plan built into it for third-party monitoring. So throughout the entire process, the adage of the cloud device being easier, often cheaper, and often more functional, whereas the local device is more costly and more of a technical challenge, with some minor improvements of security, largely holds true. So Abode is a security system and it comes with its own smart hub. The hub controls its security devices, but it does not let other devices not directly paired with the security hub to trigger its alarms. So it sets up its own proprietary wireless signal for its own proprietary communication devices. It also has a Z-Wave antenna to connect with some, but not all, Z-Wave devices. It can connect to your home phone and home computer over the home Wi-Fi network or through hardwired Ethernet. That allows alerts to be sent out to the cell phone or to third-party monitors. It has that backup data card for third-party monitoring, and it can also work locally without a monitoring subscription at all. What's interesting about the Abode Hub is the security package can be purchased not just by the year or by the month, but by the week. Some hubs are compatible with other hubs. So the Abode hub can plug into Home Assistant such that the Abode sensors, such as door and window sensors, motion detection, uh, motion alarms, anything involved with a security system within the Abode hub could also be used to drive events in Home Assistant. The Abode hub can plug in to Home Assistant. But when a security hub is plugged into an external hub, that can mean the devices that are paired with the external hub but not with the security hub directly could be prevented from triggering an alarm. So for an alarm system, it is useful to see which components are compatible with the Apple HomeKit or Google Nest or Amazon Ring, Home Assistant, Samsung SmartThings, or other generic hubs. But if you want a third-party monitored service, it is best to start with the security hub and pair any security devices such as proximity sensors directly to the security hub, and then migrate those devices into Home Assistant for additional actions, such as using the door signal, the door sensor, to not only trigger the security alarm but also turn on a light. So what do hubs really do? They manage the specific smart home devices that are directly related to the hub's purpose. Or they're a general hub that tries to manage all the devices in the home. So I can host Home Assistant on a Raspberry Pi. It's a very lightweight home automation software. The Raspberry Pi has a Wi-Fi antenna built right into it, as well as a hardwired Ethernet connection, an HDMI outlet for a monitor, and a couple other useful ports, including USB. The Raspberry Pi as a hub does not come with a Z-Wave antenna, but this can be purchased externally and then plugged into the Raspberry Pi through the USB drive. So is a Raspberry Pi with its limited computing capabilities a good enough hub? I would say that it is good enough for instantaneous monitoring. But there are a few other things to consider. First, for energy visualization and data logging, how much data is to be collected and how much hard drive space is associated with that. It could also benefit from having a backup power supply. And so for a little more money, a smart home hub could not be on a $40 Raspberry Pi, but instead be hosted on a $200 mini computer, which could also serve as a media center for the home and be backed up by a traditional uninterrupted power supply. So some smart home peripherals may require more processing power than what the Raspberry Pi offers on its own. And Home Assistant, as the software, could be installed on a dedicated larger computer instead. What's more important is how the smart home network is designed to ensure that the system is not overly complicated. So I find Z-Wave devices to be finicky. And I think they would benefit from being pre-programmed into a smart hub off-site before being delivered to the end user. At any rate, Z-Wave communication is not video or audio communication. And so it is relatively easy to communicate through a low bandwidth, low energy modem. This modem can be overpowered if you try to shove a lot of Z-Wave data through it, so it's best not to put Z-Wave to the limits. But it can network together a large number of devices wirelessly without connection to home Wi-Fi, meaning that Z-Wave devices can be pre-programmed off-site and then shipped out to the customer functional wirelessly without needing access to the customer Wi-Fi. Any smart home Wi-Fi devices would then be directly added on site. Now, let's talk through the device registration of these Z-Wave devices within the context of a smart wall plug. So these are power outlets which turn on or off based on a program command, such as time of day, or as a function of the electric load, or as a voice command, or as a simple timer. They can bring intelligence to otherwise dumb devices, and sometimes the dumber the better. The best devices are ones that start up when they get power, not ones that have to have a button pressed after they detect power. So a water heater that automatically starts boiling water when it receives power can be controlled with a timer, whereas one that cannot be set until the power is available would have less smart capability as a retrofit on a smart wall plug. So my dehumidifier is nice because it's dumb. When it has power, it turns on. When it loses power, it turns off. When it gets power back up, it starts back up again. So my dehumidifier is on a smart plug, and it's programmed to turn off right when my time of use peak metering rate starts. But I want coffee in the morning, and my winter peak rate is from 6 a.m. to 8 a.m. when I want the hot water for my coffee. So my dumb electric kettle can be left unpowered but in the on position overnight, and this allows me to preheat my hot water at 5:50 a.m. in the morning by having my smart plug turn on at that time. A push button on the side of the plug serves as a manual override. So registering the smart plug to the hub is a common task. The hub is placed into an inclusion mode to accept the device into its network. There is also a secure inclusion mode for encrypted communications, such as for alarm systems or door locks. But the encryption does slow down the communication, and so I don't recommend Z-Wave devices as security devices. The proximity sensors, the door locks, I would recommend keeping to Wi-Fi if possible, or higher frequency RF communication, such as 2.4 gigahertz, despite the added hacking vulnerabilities that come with Wi-Fi. That is because I like flooding my Z-Wave network with energy data, and the slower encrypted security communication can get flooded out by the large amount of energy use data that I'm trying to pass through my Z-Wave network. That said, I've installed a Z-Wave door lock, and the main concern is that to complete the secure pairing, the door lock needs to be in close proximity to the server. And I had built up a large supercomputer server for my Home Assistant install, which was located in the basement. And so I had to lug my server all the way up the stairs, which involved a lot of wiring and rewiring to get it to a close enough proximity to the door lock for it to pair. But then the door locks work just fine, and the smart capability of a Home Assistant powered door lock gave me an infinitely large number of possible door lock codes, keys, and scenarios to issue different users different keys. But that could have been done with a Wi-Fi door lock as well for a lot less hassle. In any event, the Z-Wave network has a maximum bandwidth it can use, and my energy monitors take up a healthy portion of that bandwidth. And so I would use other hubs or other frequency or other, like Wi-Fi to manage and monitor other devices and leave Z-Wave for energy monitoring and energy controls. This also means I don't have to host Home Assistant on a super fast computer. A Raspberry Pi is sufficient for home automation software needs unless you have a need for other computer related activities such as storing media files on a computer or storing security camera images on a computer, at which point you could build a more powerful computer to manage those functions and install Home Assistant on that as a more central build.
Energy monitors are a very interesting space, which has as much value at the commercial level as it does residentially, if not more. One of the greatest frustrations is how to get energy monitoring data from the monitor into the smart home system. Another frustration is discover that the monitor only transmits and records data for a short period of time. So a longer record, such as a record of the entire month's electrical data, needs to be programmed in accordingly. And so the hub needs additional software to display and record the energy data to make it a bit more usable for the customer. Lucky for us, there are open source data softwares that can expand the usability of our Raspberry Pi hub or other Linux-based computer. I recommend using Grafana and InfluxDB. The energy monitor itself is plugged inside the electric service panel of the home or adjacent to the panel if there's not enough room. They can be powered by the service panel breaker or by a wall plug. As mentioned earlier, getting data from these devices can be a bit of a challenge. There are proprietary devices such as Sense, which use Wi-Fi but are pricey. There are other energy monitoring products more tailored for commercial facilities or multiple branch circuit monitoring that are also pricey and might require a hardwired Ethernet connection, which is not always readily available at the electric service panel. I like using Z-Wave for energy monitoring because I can purchase a generic Z-Wave service panel monitor that isn't connected to any proprietary platform like Sense. In fact, this can be its own problem because it comes with absolutely no software, and so it will not work by itself right out of the box. It will only work when connected to a smart home hub. But this energy sensor is $90 instead of $300, and it allows for wireless communication back to the hub. And since it's Z-Wave, it doesn't require wireless communication to the facility internet to get its signal back to my smart hub. And so my entire energy manager will only be connected to the internet system at the hub itself, rather than have all these diverse wireless devices peeking into the customer's internet. And so my energy controller, by being a Z-Wave network, has fewer internet security concerns to the site host, which is perfectly fine so long as the Z-Wave network is not so complicated as to exceed its own capabilities. So as far as national electric code goes on electric service panels, it's evolving, but the basics are important. These consumption monitors can only fit inside the service panel if they do not fill more than 75% of the cross-sectional area of the service panel, which is typically a depth constraint from the back of the box to the front of the box. I think it's best to plan a power circuit and conduit pathway somewhere near the side, near the top of the electric service panel to host these service panel monitors if possible. Here is a picture of the popular consumption meter Sense. Home Assistant is compatible with Sense, so time of use metering rate could be optimized with Sense, and there's no problem with that other than the payback will be longer because Sense costs $300. Here is a picture of the popular consumption meter Sense. Home Assistant is compatible with Sense, so time of use metering rate could be optimized with Sense, and there's no problem with that other than the payback will be longer because Sense costs $300, whereas the actual hardware required for the same data could be had for 1/3 that amount. But at the end of the day, you're ending up paying for Sense's code or having to figure out how to do the code yourself.
First, the consumption monitor is installed inside the electric service panel. Because I rent, I'm running the power monitor to an external power outlet out the bottom of the service panel. But it could easily be powered within an available breaker space. The user manual is consulted to confirm the orientation of the current sensing transducer clamps, and it is noted that the power supply must be on the first leg of the power of the first clamp. If the power outlet is powered by leg 2, I would reverse the clamp orientations. The smart hub is then placed into inclusion mode. I'm not using this hub for security devices, and so I will not be using the pair secure option. After inclusion, the device shows up as a node in the